with actually an award winner. So Syntiant won the product award in tinyML. Don't know if you saw it. Yeah, it gives me great pleasure to introduce Sean McGregor, who's going to talk about this product in this the first presentation in this section. This section, we're going to have 12 minutes per each talk. So about 7 minutes of presentation, about 5 minutes for discussion. So take it away, Sean.
Thank you. And I promise if you saw the presentation on Monday that there is new material, but the first slide is going to be much the same since motivation is the same. Largely that the modelers in our community have had quite a challenge going from the cloud space actually down to the silicon. That's really what the tinyML community is largely about, is figuring out a way to go from that largely resource unconstrained environment down to our highly constrained environments. And Syntiant, we solve this problem very deliberately through a co-design process where we bring together deep learning engineers and silicon designers to produce silicon that can make that process as light and easy as possible. And I'm going to label this as kind of the NDP 120 is really doing this co-design process without compromise. It's producing NDP 120, which is meant to run your architecture your way and really open up that design space. And to ground this in the specific example, this is a typical tinyML solution pattern of doing a cascade architecture where you have a sequence of models, increasing complexity, increasing compute requirements. There's a front-end model that's listening to audio all the time. It's listening for something like Alexa. And then there's going to be a confirming model one that's running on the application processor or bigger footprint there. And then that gets handed off to the cloud, which has yet a larger model, typically running on a GPU, and that is confirming model 2. And the question to ask here, just operationally, is can we actually update confirming model 2 after we already have models in the field? The answer here, of course, is yes. I've actually heard reports at some companies update their models as fast as every 10 minutes, maybe tuning, maybe some retraining. But can we update confirming model 1? And the answer here is also yes, but if we do update that, we have to update the model running in the GPU in the cloud as well. Can we update the front-end model, though? And for this, I'm going to dial in a little bit more in depth and say that if we update the front-end model, we have to update 3 jointly calibrated and tested models, and we have to evaluate those across a set of attributes and performance. We also need to manage the simultaneous deployment of update software to models that are already in the field across the microcontroller, across the application firmware, the cloud model. And very often these involve multiple parties that are each responsible for different elements of the solution. So this is really, in the machine learning community, what we call a model entanglement problem, and what's more kind of a dependency hell, that all these problems are solvable, but just logistically bringing it all together is quite challenging. The ideal solution here would be to just kind of vacuum all those models up into one footprint. Here I put it inside the NDP 120's block, but the problem here is this is not possible because it needs to be tiny if it's running in the front end of the solution stack. But what is tiny at this point? And to explore this question, I'm going to bring in the OKG model, which is engineering activity that we were looking at in the past few months. And this is a model that's running on billions of devices. Google really has a run it or leave it philosophy for it. They don't really want to retune their collective system for every device that they ship. So we had to get it running on the NDP 120 as it is, or it doesn't matter, at least from Google's perspective, and it must be low latency, low power, or it also doesn't matter. So can highly specialized edge silicon like the NDP 120, where we do a lot of intentional low-level design to optimize, really run the OKG model? And then what's more, is there room for more? Can we do more than just the OKG model? And let's see how the engineering effort turned out here.
You can see the live demo monitoring the power supply and recognizing, okay, Google. Okay, Google.
So we got it running. We got that take it or leave it model running, and what's more, it's actually clocking in at 280 microwatts. So actually a very strong performance point. In fact, the lowest power implementation of OKG in the world. Uh, what's more, though, the really critical point here is that only 3% of the neural core is actually utilized in the course of processing this model because it's really a tiny ML model built for the tiny ML world. And what this means in the NDP-120 is if we're if we consider this Google model to be a front-end model that's only using 3% of it, then we can use 20% for some confirming model 1 that's more power intensive, that runs conditionally, and we can then use yet more of the system resources towards a second confirming model, or the thing that would more typically have been running on the GPU. So there's a really big room to grow that is really not, that is only tiny in its power consumption and those elements, but not in its capability and modeling space. But how did we do this? And I'm running a bit low on time, but I'll say that shipping 10 plus million prior generation chips was extremely helpful in coming together in this solution design and producing a neural accelerator that's highly efficient, highly specialized, and a DSP that is really provides the general compute capabilities and allows for running things like the arbitrary OKG models and opens the software design space. Which is also a lot more open for the modeler because we actually brought together the modeling environment and into the chip design process. So TensorFlow is actually running inside our chip design tools and telling us whether we're bit matching, and that same reference point is actually inside our software when we ship it to customers. They can run in TensorFlow a chip sim that additionally gives the full performance properties of the chip. So you can actually look on a per layer basis, cycles, energy, parameter utilization, and modelers can then negotiate with system properties rather than asking 20 questions of the embedded team to figure out what is or is not possible. From here, I have 2 more videos that go into the flexibility of the chip. I'm basically at time at this point, so I'm not gonna I'll play both of them and just say this is a video I recommend you watch that shows running 2 different models. One is a Glassbreak model, one is a wakeword model, and they're both able to run. And then we also have a kind of stress testing far field case that I quite like. So in summary, the NDP-120, it's highly flexible. Bring your models, get to run on our silicon, and we'll see about getting you under that milliwatt magical number that we so like hitting at Syntiant. And we hope you'll really redefine in your head what is possible at the front end, at the tinyML side of things with silicon. And thank you, and I'll flip over to questions.
Thank you very much, Sean. Do you have any indication or any number to for us to be able to compare? I mean, clearly it sounds very impressive to do this OK Google with such low power. How big is the model you're running, and how much power would it have costed on, let's say, a traditional MCU compared to what you have?
On that, I am not prepared to answer, mostly due to wanting to maintain the good feelings and engineering effort, and this being the elements that I'm permitted to say on that particular effort. So I can say we're the best, which is probably unsurprising, but I can't go into comparison elements.
Okay, and do you do any network transformations based on, let's say, you show that you can get from TensorFlow? Do you take that model and modify it in some ways to make it fit, or not fit, but give you optimal power performance, for example?
I'll say that there's a variety of things that we can do in the chip to make it more power efficient. That's mostly customizing it to be a runtime that is aware of the exact workload that it's running. But when it comes to the task that's being performed on it, we actually need it to be behaviorally consistent with what is already in the world and not running on our silicon. So there's a set of things we can do to make it run better and to really get that number cranking as low as possible. But we can't do things like leverage properties of sparsity that aren't leveraged elsewhere, and because that changes the behavior of the system in subtle ways that they want us to look just like everything else in their ecosystem.
Yeah. Okay. And actually, I have a follow-up question, which is was a nice segue to it. We have a question here from one of the audience saying that they work with NDP 101. I presume is a previous device. Will that work be transferable to this new silicon?
Definitely. There's ability to directly port it over. There's also a lot of capability of repackaging those networks to leverage what you see up on this slide of variable parameter precision, for instance. So the NDP 100, you're going to be running in 4-bit weights. If you find that you want to increase the model size to use a little bit more of the footprint in the NDP 120 that's in there, you can say like input layer run at 8 bits, which input layers often need to be at higher precision, and then you can push towards lower precision. In the later parts of the network, then basically it's opening the design space, even if you have a model that's trained in the NDP 100, and you can do a lot of clever things in it that I'm quite happy about.
Okay, one final question. It's a tough one because it's from Kurt. What are Syntiant's plans for tackling more challenging applications such as larger vocabulary, speech recognition, or even natural language understanding?
So I don't think I'll bring up too much of like the next silicon plans, because I'm not sure what Kurt will be happy with me saying there, but I will say that the NDP 120 is capable of larger vocabularies as compared to other solutions at the power point that's operating at. It also allows for a lot more complicated models, language modeling and such, like pushing towards decomposing words into their more base parts or phonemes, and then having more flexible interfaces as a result. So I think you can expect to see a lot more running both on the NDP 120 here, and then only more in the future.
Okay. Well, thank you very much, Sean.
Again, just a quick shout out to our sponsors. Bear with me for 1 minute. We have different categories. We have executive sponsors. First one being ARM. Then we have Qualcomm. We have Samsung. Platinum sponsors. ADA Compute. Lattice Semiconductor. Gold sponsors. BrainChip. Babel Labs. DSP Group. Edge Impulse. EMSA. Gray Matter Labs. Greenwaves. Hymax. Imagimob. Latent AI. Maxim Integrated. Quixo. Reality AI. SensiML. Silicon Labs, Syntiant, Google TensorFlow, XMOS, and lastly, silver sponsors, Edge Cortex, Hotg, and Synsense.